The universe is built on many principles that we know of, that are like the rulebook of how things can react and coexist. So what I want to do in this video is present a high-level overview of the four fundamental forces of the universe, and I'll start with gravity. It might surprise some of you that gravity is actually the weakest of the four fundamental forces. This is quite surprising because most people would think that it's what keeps us from jumping off the planet, it's what keeps the moon in orbit around the Earth, and the Earth in orbit around the sun. And it's even what keeps the sun in orbit around the center of the Milky Way galaxy. So it's a little bit surprising that it's actually the weakest of the forces, and that will start to make sense when you actually think about things on maybe more of a human scale or molecular and atomic scale. Even on a human scale, you have some type of gravitational attraction, but you don't notice it. You don't see them being drawn to each other the way you might see two magnets drawn to each other or repelled from each other. And if you go on an even smaller scale, you see that it matters even less. We never even talk about gravity in chemistry, even though there still is trace amounts of gravity there. At those scales, the other forces really start to dominate, so gravity is our weakest. The next force that we'll move on to is maybe the hardest force for us to visualize, and that is called the weak force. It's quite an ironic name because the weak force is not even the weakest force, as we just learned. The weak force is sometimes called the weak interaction, and it's what's responsible for radioactive decay. And in particular, it's responsible for beta minus and beta plus decay. An example of the actual weak interaction is if I had some cesium-137. Most people are going to have no idea what cesium-137 even means, so we'll assess that first. Cesium is the 55th element on the periodic table, which might be a given, but what is the 137? Well, 137 means it has 137 nucleons. So what is a nucleon then? A nucleon is either a proton or a neutron. Those two subatomic particles are found in the nucleus, hence the name nucleon. So if you add up the protons and neutrons of cesium, you get 137. And we know it's precisely cesium because it has exactly 55 protons, making it the 55th element. So with that information, we know that the nucleus of the cesium has 55 protons and 82 neutrons. So the weak interaction or weak force is what's responsible for one of the neutron's quarks flipping and turning into a proton. I'm going to go into detail about what a quark is and all of that, and the quantum theoretical math can get pretty complicated, but I just want to give an example of what the weak interaction does. So if one of these neutrons turns into a proton, then we're going to have one extra proton. We still have the same number of nucleons, but instead of an extra neutron there, we now have an extra proton. So now since the proton defines the element of an atom, this cesium atom is now a different atom. It is now barium, which is the 56th element. And what this will do is it will actually emit an electron and an anti-electron neutrino. I'm not going to go into the details of what an anti-electron neutrino is, as this is now very, very advanced quantum theory that we may or may not get into later down the road. But these are all fundamental particles, and this is just what weak interaction is. It's not something that is completely obvious to us, and it's not the kind of traditional pulling or pushing away from each other as we would associate with the other forces. Now, just to give a sense of how weak gravity is, even relative to the weak interaction, the weak force is 10 to the 25th times the strength of gravity. So you might be wondering that if this weak interaction force is apparently so strong, how come this doesn't operate on planets, or us, relative to the Earth? The reason why this doesn't apply to intergalactic distances the way that gravity does is because the weak interaction only applies to very, very small distances. As a result, it can be much stronger than gravity, but only over very small distances. So it mainly only applies to the subatomic scale. If you apply to anything beyond that, it kind of disappears as an actual force. Now the next force up the hierarchy is one that we are more familiar with. It's something that actually dominates most of the chemistry that we deal with, specifically the electromagnetism that we deal with, and this is the electromagnetic force. To give a sense of the strength of this force, this is 10 to the 36 times the strength of gravity and 10 to the 11th time stronger than the weak force. So this is unbelievably strong, but once again, the electromagnetic force does not apply over macro scales like gravity. There's nothing about the electromagnetic force that stops it from doing this, and technically it actually does apply over large distances, but in reality though, there aren't huge concentrations of either Coulomb charges or magnetism in the way that you do with mass. Since with mass we can have huge concentrations of it, it can operate over huge distances with forces way weaker than the electromagnetic force, such as gravity. Since the electromagnetic force is both attractive and repulsive, it tends to kind of sort itself out. So you don't have these huge concentrations of charge force in our everyday lives. Another thing that you might be questioning is why exactly is it called the electromagnetic force? There are things like Coulomb force or electrostatic force which we're familiar with. Positive charges or like charges want to repel and different charges want to attract. We've seen this multiple times, and this is what the Coulomb force or the electrostatic force is at its essence. So now we know what the electro part of electromagnetic means, but what is the magnetic part? You've probably used magnets on your fridge, and what you may have discovered is that if you put the same side of the two magnets towards each other, they're going to repel each other, and if you put the opposite sides, they're going to attract each other. So why is it called one force? It's called one force because it turns out that the Coulomb force and the magnetic force are actually the same things in different frames of reference. So this is obviously an oversimplified conclusion, but with a little more complications and details, magnetic forces and electrostatic forces are very similar forces in different frames of reference and scale. Now the strongest of the forces is probably the best name of them all, and that's because it's called the strong force. Although you probably haven't seen this yet in any chemistry class, it actually applies very strongly in chemistry. It's even applicable in the very basics of atoms. For example, a helium atom has 2 protons and 2 neutrons, and then it also has 2 electrons circulating around. One question that may or may not have jumped into your mind when you first saw this model of an atom is that we see the electrons are attracted to the nucleus as it has a negative Coulomb charge, and the nucleus has a net positive charge. But what's not so obvious is that these 2 positive charges are sitting right next to each other. If the electromagnetic force was the only force in effect, the protons would just repel each other. And so the only reason why they're able to stick to each other is that there's an even stronger force than the electromagnetic force operating at these very small distances. So if you get 2 of these protons close enough to each other, then the strong interaction takes its role. You now have the strong interaction actually keeping these charges together. And once again, just to keep in mind, relative to gravity, it is 10 to the 38th times the strength of gravity, or it's about 100 times stronger than the electromagnetic force. So once again, the reason why you don't see the strong force, which is the strongest of all forces, applying over huge scales is due to their strength dying super quickly when you increase the scale of the forces. The only one of these 4 forces that can operate on large spans of distance and area is the gravitational force. In gravity, you have one mass and another mass, and they attract each other. Then you have another mass that's even better at attracting other masses, and so it'll keep attracting things. And this snowballs the process, and that's why gravity can operate on these really, really large objects in our universe. So as we learned in this content-heavy video, there are 4 fundamental forces that we see in our universe, which from weakest to strongest in order are gravitational force, weak force, electromagnetic force, and strong force. These 4 forces will repeatedly come up in the unit of astronomy, and even in other sciences such as physics and chemistry. They form the very basis on which our universe is built, and are very important to understand in order to get further into the complex, mind-bending field of astronomy. In the next video, we'll give ourselves an introduction to the Big Bang. But for now, I thank you all for watching.